Thank you so much for that introduction and also for the opportunity to share my work. So I'm Nettekoven. As Gunnar mentioned, I'm a researcher in Oxford and I'm interested mainly in the role of GABA in adaptation. I did my PhD with Charlie Stagg and Ned Jenkinson here in Oxford, and I'll be presenting part of my PhD work in which I link M1 GABA to retention of an adapted state. So motor adaptation is fundamental to navigating our world because our environment and our bodies constantly change, and to keep up performance, we're required to adapt to this change. So for example, since you've all had to recently work from home, you might have had to get used to using a different computer mouse. And this mouse might have different properties such as a lag, and you will start make movement errors in the beginning, like you can see here on the graph in the red curve. But you quickly adjust your movements to those new properties of your mouse, and your performance will return to former levels. Then once you've returned to your department mouse after some delay, you'll start making movement errors again, this time in the opposite direction. And this is because you retained some of that compensatory movement. So in my talk, I'll be referring to the phase where people change their movements in response to a perturbation as the acquisition of an adapted state. And then I'll be referring to the phase where the perturbation is removed after some time and people display an after effect that is gradually reduced as the retention of the adapted state. Now, there's a framework of adaptation that suggests that the acquisition of an adapted state adaptation task primarily involves the cerebellum, whereas the retention of this adapted movement relies on M1. And this is in contrast to other forms of motor learning, such as, for example, motor sequence learning, which is thought to primarily involve M1 at the acquisition stage. Now, in motor sequence learning, we know that GABA concentration measured from M1 early correlates with acquisition of a motor sequence. So we therefore hypothesize that in adaptation, where M1 is involved in retaining the adapted state, early M1 GABA concentration would correlate with retention. And then secondly, it's been shown that functional connectivity between left M1 and the right cerebellum changes after performing an adaptation task. So specifically, the activity in left M1 and right cerebellum becomes less synchronized. So here you can see pre and then post. So there's a decrease in the connectivity. So then we also wanted to test whether retention would correlate with the change in connectivity between left M1 and right cerebellum. So in order to test this, we had 15 healthy right-handed participants attend 2 MRI sessions where they were either scanned during a rotation task or during a control task. And I'll show you the rotation session first. So inside the scanner, participants controlled a cursor on the screen using this joystick with their right hand. They were instructed to hit one of 8 targets. So one of them you can see here. And this would be the optimal movement, and this would be the slightly imperfect movement that the participant needs. Now, after these baseline trials, we would impose a 10-degree rotation. So you can again see optimal movement, participant movement, and this time this is the visually rotated feedback. And we would increase that rotation every 40 trials by 10 degrees. So we end up with a 120-degree rotation at the end of the session. Then outside of the scanner, after some delay, we took the rotation away to assess retention of the adapted state. To look at M1 GABA, we collected magnetic resonance spectroscopy data from a voxel positioned over the left M1 hand area. And we also collected resting state fMRI data before and directly after performing the task. Now, the only difference to the control session was that in the control session, there was no rotation imposed at any point during the task. So here I'm showing you the MRS blocks acquired from the left M1 hand area, and each block consisted of 53 spectra that were averaged. And the block where we got our early measure of GABA from was this baseline block. So where people are not yet performing any kind of differential task between the sessions. Then I'm showing you the voxel placement here. So between sessions and between participants, across sessions and across participants, we got quite consistent placement of the voxel. And I'm also showing you the raw spectra that we're getting and the fit of the spectra. So we quantify GABA by fitting a linear combination of the spectral contributions that we expect to be there in the MRS voxel. And from this procedure, we obtain our GABA measure. Now I'm showing you the behavior here. So what you can see in blue is the control session. People are just fluctuating around 0. And then in the rotation condition that you can see in red, when we impose the rotation, people make a 10-degree error, but they actually manage to reduce their error quite consistently over the course of the experiment. So from this phase, this main task phase, we got a measure of the adapted state by just calculating the average angular error. And then from here, we're getting, from the rotation condition, we're getting early during the washout period, we're getting a measure of the retention of the adapted state. Now, what we wanted to check first, because it's a slightly unusual adaptation paradigm, was to see whether we're actually driving changes in the brain that are known to occur in response to adaptation. So specifically, we set out to replicate this paper by Albert and colleagues, where they show that after adaptation, but not after control, the functional connectivity of a cerebellar network is increased. So in our experiment, that's exactly what we also find. So I'm showing you here in magenta the cerebellar network just as a mask. And what you can see in red and yellow are voxels that are increased after performing the adaptation task compared to after performing the control task. To also test the specificity of this result, we ran the same analysis on the default mode network where we didn't expect any kind of changes, and indeed we didn't find any changes. What we also did was then extend this analysis that Albert and colleagues did by looking inside the rotation condition and seeing whether we can find a relationship between the strength change of that network and the actual adaptation performance. And that's what we're finding. So what you can see here is people having a lower error, so performing better on the adaptation task, they also increase the strength of the cerebellar network. And we don't find any kind of similar relationship for change in strength of our control network, and these are significantly different. We also looked at whether our results hold when we quantify adaptation using a commonly used state space model, so model-based approach to quantify adaptation performance. So we modeled the adaptation performance on this task using a single state model. And we find that our model-free and model-based parameters of adaptation correlate highly, and that our results hold for modeled adaptation as opposed to just an angular average error. So that gave us some confidence that we're actually driving changes in the brain that are known to occur in response to adaptation, and that our measures of adaptation, it doesn't matter how we quantify adaptation, the same results hold. So next, we actually tested our specific hypothesis regarding early M1 GABA and retention of the adaptive movement. So what we find is that M1 GABA measured at baseline correlates with retention, but not with adaptation. So the higher your M1 GABA concentration at baseline, the more you retain of the adapted state later after adaptation. We also see that the change in connectivity between left M1 hand area and the right cerebellum, this change in connectivity also correlates with retention, such that if you decrease, the more you decrease your connectivity, the more you retain of that adapted state. And then lastly, what we see is that there's a relationship between M1 GABA and this change in M1 cerebellar connectivity. So kind of having a threefold relationship between the three measures. And this relationship does not exist between the neurotransmitter and change in connectivity for a control neurotransmitter, which is glutamate in this case. So because we got this threefold relationship, we wanted to further explore this data and therefore calculated a mediation analysis. So a mediation analysis tests whether the observed direct relationship between two variables, so in our case, M1 GABA and retention, might be mediated through an indirect pathway. So in our case, M1 cerebellar connectivity change. And that's exactly what we find. So our mediation analysis showed that the relationship between M1 GABA and retention was mediated by this indirect path, so connectivity change between left M1 and right cerebellum. So to go back to our original question of what is the role of M1 GABA in retention, this is the kind of model that emerges. So higher M1 GABA concentration before adapting relates to a decrease in M1 cerebellar connectivity, which in turn relates to increased subsequent retention. So just to summarize all of this, I showed you that our adaptation task, adaptation increases connectivity in a cerebellar network in a way that is performance relevant. we find that there's a relationship between early M1 GABA and retention of an adapted state. And we also find that this relationship is mediated by the connectivity change between left M1 and right cerebellum. So with this, I'd like to thank my supervisors, Charlie Stark and Nick Jenkinson, for all their support, my lab group for their help, and of course, thank you to everyone who was listening. Thanks.
Well, thank you so much, Caroline. That was fantastic. Also, thanks very much for sticking to the timetable. We have time for a couple of questions. Are there any questions? Please feel free to get in touch. Use the question tool here. Okay, there's one question here, which thanks, Caroline. Have you guys also looked at networks between the cerebellum and the posterior parietal cortex? From Takeshwar Singh.
That's a very good question. I think it's an interesting question to address. We haven't looked at this yet, but that is something that we could do with our functional connectivity data. And certainly, I think the posterior parietal cortex would be an area that is likely involved here. But no, we haven't looked at this yet.
Are there any further questions from the audience? Yes, there is another question here from Nick Kitchen. It says, thanks, Caroline. Great talk. Is there any reason why you chose a stepwise permutation paradigm instead of a consistent rotation?
Yeah, that's a good question. Because I think the reason that we went for this kind of paradigm was really because we wanted to drive adaptation throughout the whole period of the experiment. Because as you can imagine, we were also trying to find out whether there might be any kind of change in GABA during this adaptation period, which we didn't see. And in order to see this kind of change in M1 GABA, you have to really give GABA basically time to catch up. So in a sense, drive the process throughout the whole time. So we really wanted to dissociate retention and adaptation here, and therefore wanted to be sure that we're driving adaptation for long enough to these changes to actually emerge.
Fantastic, thank you. There are a couple of more questions.